volume of 0.1 meters cubed containing 1 kilogram of liquid water with air in the headspace of 101,325 pascals and 298 Kelvin. So first I'm going to draw out what the container looks like. So the container looks like this. And there is H2O inside. And then I'm going to just write out our initials that we have first. So our total volume is going to be 1.1 meters cubed. And then we have our mass of our water, which is 1 kilogram. And then we are going to have our pressure initial, which is going to be 101,325 Pascal. And then our temperature initial is going to be 298. Okay, so next is going to be what is the temperature should be when the pressure is raised to, so our pressure is going to be 200 times 10 to the third pascals. What is the temperature going to be at that initial constant? Okay, so what is the temperature going to be? So we're trying to figure out what temperature is. And then our container over here is closed. Okay, so what we're going to do first is we're going to try to figure out what our volume of the air is, or the volume of our vapor. So total volume equals the volume of the air plus the volume of the water. Okay, so our mass of water. So 1 kilogram, 1,000 kilograms equals 1 meters cubed. So that is just going to equal total. Total is going to be 0.1. And then our air, we don't know our air, we're trying to figure out the air. And so then our water is going to be 1 over 1,000, which if you do units to make it decimal, it's going to be 0.001 meters cubed. Yeah. So then that makes V air equal 0.099 meters cubed. Okay. Next. So just like volume, pressure is going to be the same, where that pressure total is going to be the pressures of water and the vapor. So let's write over here, our pressure total equals the pressure of our air plus the pressure of H2O. Okay, so I'm going to do pressure of air. Okay, so here's the pressure of our air here. So our pressure of our air. So air is an ideal gas. And well, our vapor is an ideal gas. So we can use our ideal gas law, PV equals nRT. So this is P air, so the moles of air. R is our R constant, T, and this is going to be at where our pressure is final. So our T is going to be our T that we're trying to find, not our T initial, over the volume of our air. Okay, so that's it. But we don't know the moles of our air. So we're going to have to figure that out and try to cancel some things. So while using the ideal gas law, we're going to figure out our in air. So our pressure, this is going to be when our pressure is initial because we want to figure out how many moles it is. So next, we're going to do our volume. This is going to be our volume of air over our R constant, and then our T at initial. Okay, so when we place air into here, we get some cancellations. So our V's are going to cancel out, our V airs, our constant's going to cancel out, and that's going to leave us with the air is going to equal pressure initial over temperature final, temperature initial. Okay, so now next we're going to try to find is the pressure of our water. So this is going to be the pressure of the saturation of water, which is the pressure at the equilibrium curve. And that's when we're going to use Anton's equation. So Anton's equation is the log base 10, the pressure, saturation, water, equals A minus B over T plus C. Okay? So we want to get pressure by itself, so we're going to have to raise everything to the 10th power. So the log cancels out. So we have P okay. And so that is going to be our pressure of water, or pressure at the equilibrium curve of water. Okay, so now we're going to want to make this equation equal to 0, because when we put this into our code, we're going to want to find roots of it. And when you want to find a root, it has to equal to 0. So we're going to subtract over P total. P total is going to be our P final. So this should make an easy equation of Pi over T over Ti plus 10 to the A minus B T plus C minus 200 times 10 to the third pascals. But I'm going to take the pascals out of that actually. Okay, so this is our equation right here. And then I'm going to help you, and I'm going to solve it in NumPy. I'm going to solve it in Collab. So let's start coding it. Okay. Share my screen. I don't want that. The import NumPy as NP, and then import SpicePy as optimized, and then we import root. Okay, so what we're gonna want to do is we're gonna put in our initials first. So our volume total is gonna be 1 point, and then I'm gonna put the units in here because units are gonna come in important later. Our TI is going to equal is Kelvin. Then we have our pressure initial, which is going to equal and then we have initial, pressure initial, and then we have our mass of H2O, which is 1 gram. And then if there's any other, and then our pressure final. PF equals 3,000. Okay. This is going to equal, and I'm actually going to put decimal point in all of this so that it becomes a float, not an integer. I want it to be a float. So we're going to make them all P's. Okay. I think that is all of our initials from the board. So next, let's start on our equations. Okay, so first things first, I want to do Anton's equation to find the pressure of air first. So I have Anton's equation pulled up here, and I have all the A's and B's and C's because I can't remember that offhand. Why is that? Okay, so what we're going to want to do is we're going to define the function. We're going to define, because this is going to be our vapor pressure, so it's going to be Pvap, and this function is going to be defined T. So now we're going to want to put return, because we want it to return our equation. So it's 10, and then it's A minus E divided by, and we're going to subtract T by 273 because Anton's equation is going to be in millimeters mercury and Celsius. And we have Kelvin right now, so we have to convert that. So then you multiply by C. And I think we need one more parentheses from that one. That should be good. Let's see if this, there should not be one more parentheses on that. Okay, cool. Now let's get to our another code. So on this one, I'm gonna put in the V totals. So I wanna calculate V air minus, and then I have mass of H2O divided by 1,000 because we want to convert that into meters cubed. Okay, and now let's type in the moles of air, just because I know we're going to need it later. Right now we don't need it. So the moles of air are going to be, since PV equals nRT, got a board, our air is going to be PI multiplied by our V air. So V air divided by, and then we have our R constant. Actually, let's put our R constant up here. R constant equals 1 to 4. Let me look up the R constant. R constant. The R constant is 3.14. Okay, pretty close. Pretty cool. Okay, so then we have R times the T initial. T initial. Okay. See if that works out. It doesn't because is V total is not defined. That's interesting why V total is not defined. Oh. Okay, there you go. So that works. So let's code some more. Okay, so now I think we're gonna do is Anton's equation. Well, not Anton's equation, but I'm just gonna define a random equation as Anton's equation. It's gonna be our pressure equation that we have here. But I just like to say Anton's equation for some reason. So Anton's equation, and it's going to be derived of T. So we want it to return to us. We're going to want to do is Pvap T. Pvap of T minus, we have Pvap, and now we're going to want to do is our PI, and we're going to want to divide it by our PI, we're going to want to divide it by 360, and then this multiplies by T divided by TI. which is up on the board. And since those will cancel out because they're by the same denominator, like if you subtract it by 275, that's not going to change anything with it kind of being like a ratio. So that should be fine. This is actually a plus sign, and this is going to be plus. Plus our V final. Do I have V final up here? Yeah, I have pressure final divided by 760 to get it back into millimeters of mercury. So we run the code, it works. Okay. Next, what we're going to want to do is we're going to want to find the root. We want to find the root of t. And the equation we want to do is the Anton equation that not Anton's, but like the equation that I defined. Okay. And now we just have to type in a guess. I'm going to type in 350. I like 350. Okay. Right here. So that should work. That should work. That doesn't, why did that not change anything? Oh wait. Okay, so here is our equations. And here is our root. So next, part 3 of B. And I'm going to stop sharing my screen. My screen. So, okay. So it says, repeat the calculation. So I'm going to try to remove this over here. This is not needed for what we're going to do right now. Okay, so it's saying when there are 0.3 moles of water vapor desired, but we don't know the total volume. Okay, so what they're asking for is, since they're asking for the water vapor, that is an ideal gas. So we're going to use our ideal gas law. Okay, so the moles of air are going to equal the pressure. Now this pressure, since it's the moles of water vapor, this is going to be the pressure of H2O. And this is going to be at the equilibrium curve or the saturation line. And then you have your volume, going to be your volume of your air, over. You're going to have your R constant, and then your T is going to be your T final. Okay? So, and this is going to all equal 0.3. Okay? So now we're going to use this and what we just did, and we're going to figure it out. And we're going to code. So let's get back into collaboratory. Okay. Let's share my screen. Okay. So what we're going to do is let's code another. This is, I'm going to define it as B4. Define as, because this is B number 4. I'm going to just do function. And this is a vector. Okay, so when dissolving, since there are 2 unknowns, you're going to have to use a vector because we're going to have to figure out 2. Okay. So it's going to be V total, and it is going to be vector. Vect equals T, or T equals vector. T equals vector, sorry. Okay. Now, since our volume of our container is not known, we're going to have to figure out, we're going to have to put in this because all of this stuff is going to be changing. So we have to put it into this right here. Let's just tab over. Okay, so what we want it to return is we want it to return kind of a list. We want to do a list. And our list is going to be, first, it's going to be our N air, right? Our N air, but we want to find the T and the V air in it, since we don't know that. So those are going to be our two things that we don't know right now. So what we're going to do is N air is vapor pressure. This is vapor pressure at T. And this is going to be multiplied by our V air here divided by our R constant times our T. Okay, I think that is going to be orders of operation approved. And then we're going to subtract this by 0.3 because we want it to be a root. So it has to equal to 0. Okay, now what we did right here is going to be the same thing. Okay, so now let's code to return it. So our root function, right? So first we're going to want to do is the function we have. So b, okay, it's going to be b4 function. And we want to put this in to whatever, we want this to be a list. So since I did temperature first, and then we're going to do, I did temperature last, and I did pressure and volume first. So I'm going to do 0.1 because that was our pressure. That was our volume last time. And now I'm going to do like 250, 350 again. And we get our answer. So this is what it's around. Our solution converged. So here it is for our volume and then our temperature. So thank you. That should be done with question. That should be done with question. That should be done with homework 1, part B. Thank you so much.